to motivate the concept, you look at part 2. In part 2, we are trying to introduce the meaning of indefinite integrals. Okay, so just follow me. We'll work on the questions one by one. Now you look at part 2, question 1. In part 2, question 1, I'm looking for which function has the derivative of cos of x. Anybody want to tell me the answer? Write the answer on in the chat. Which function has the derivative of cos of x? You know that. So please try to answer the question, please. So the answer to question 1. Which function has the derivative of cos of x? So please. It's sine of x. It's sine of x. It's not negative. Yeah, it's sine of x. Okay. So the answer to question 1 is sine of x. The answer to question 1 is sine of x, right? So because you take the derivative of sine of x, you have cos of x, right? And question 2 is essentially the same thing as question 1. To do the integration, we need another term. The term is called antiderivative. Antiderivative. Now, in question 2, to get an antiderivative of cos of x, you just think which function has the derivative of cos of x. So, in question 2, so the answer, again, in order to answer question 2, we are looking for a function with the derivative of cos of x. So basically, which function has the derivative of cos of x? So the answer is also sine of x. In this unit, we need the concept of both the derivative and the antiderivative. Okay, so don't be confused. The derivative of sine of x is cos of x. We have learned that before, right? The derivative of sine of x is cos of x. So because of that, we also say sine of x is an antiderivative of cos of x. Integration is kind of a reverse operation as differentiation. I want to repeat the term, okay? Cos of x is called the derivative of sine of x, and correspondingly sine of x is called an antiderivative of cos of x. So we're just done question 2, right? Any questions so far? I just introduced a new name, a new term. What do we mean by an antiderivative of a function? Okay, now let's try another one. Anybody want to tell me an antiderivative of x squared? Later on, we are going to have a formula. The formula is also called the power rule. But now I'm looking for an antiderivative of x squared. You think which function has the derivative of x squared? If you can find that function, then the question mark is the antiderivative. It's a antiderivative of x squared. Anybody want to guess the question mark? Later on, I'm going to tell you the general formula. But if you can guess a function, then you know the concept. Anybody want to tell me that? You take the derivative of what function you can get x squared? A little bit hint, it has to be a number times x cubed, right? The problem is which number times x cubed. You take the derivative of what number times x cubed is equal to x squared. Anybody want to tell me the question mark? I'm looking for an antiderivative of x squared. By that we mean I'm looking for which function has the derivative of x squared. You know that. some number times x cubed. So what number times x cubed, please? Okay, it's 1/3 times x cubed. Okay. Okay, now let's try to verify that. Okay. You take the derivative of 1/3 and then times x cubed. You leave out 1/3. You leave out the constant of 1/3, right? And then you take the derivative of x cubed. So you have 1/3 of 1/3 times the derivative of x cubed is equal to 3 times x squared. So do we see 3 and 3 is cancelled? I'm trying to say, you look at the mouse cursor, the derivative of 1/3 times x cubed is equal to x squared. That's why 1/3 times x cubed is an antiderivative of x squared. So does that make sense? So don't worry. So later on I'm going to give you the general formulas. So today you have many formulas to memorize actually. Actually, if you know what's going on, you do not actually need to memorize too many things. So you know what I mean soon. Okay. Okay, now let's move on to question 3. Okay. We have seen sine of x is one particular antiderivative of cos of x. I want to repeat, we have seen sine of x is an antiderivative of cos of x because the derivative of sine of x is equal to cos of x, right? In question 3, I'm looking for two different antiderivatives of cos of x. I'm trying to rephrase the meaning of question 2, okay? Again, the meaning of question 3 is that I'm looking for two different antiderivatives of cos of x. Sine of x is one of them, so we'll count that. Okay. Anybody want to tell me another one? Another antiderivative of cos of x? Anybody want to tell me another antiderivative of cos of x? It's actually a simple question. If I tell you the answer, then we'll know what's going on. Okay. Actually, another different one, you can just take sine of x and then plus any constant. So now let's say plus 1. Okay. So because the derivative of a constant is equal to 0, I'm trying to say sine of x plus 1 is also a antiderivative of cos of x because you take the derivative of sine of x plus 1, you have cos of x, right? These two functions are different, right? So that's how we answer question 3. We found the two antiderivatives of cos of x. I mean two different ones, two distinct ones. Distinct means different, right? Okay, so that's question 3. Simple. Now let's move on to question 4. Okay. In question 4, we are looking for all the antiderivatives of cos of x. In question 3, we found the two particular ones. Okay. In question 4, we are looking for all the antiderivatives of cos of x. Anybody want to tell me the answer? From question 3, you can guess the pattern. I think you can guess the pattern. In question 4, we are looking for all the antiderivatives of cos of x. Sine of x is one of them. Sine of x plus 1 is another one. Actually, in question 4, we are kind of looking for the general form of all the antiderivatives of cos of x. Okay, so the answer to question 4, I'm going to tell you the answer to question 4. I'm telling you the answer, it's simple, right? So the answer to question 4 is sine of x and then plus c. You can plus any constant, right? You can plus 1, you can plus 2, you can plus 0.5, you can plus pi, you can plus e. Okay. As a matter of fact, c can be any constant. To answer question 4, you'd better write something like c C can take any constant. Okay. C is an arbitrary constant. Okay. That's how we answer question 4. Now look at question 5. In question 5, we are looking for the most general form. The most general form of the antiderivative of cos of x. Actually, the answer to question 5 is kind of the same thing. Okay. Sine of x plus c. C is an arbitrary constant. This is indeed the general form of the antiderivatives of cos of x. So the answer to question 5 is the same thing. I'm just trying to use different terms to tell you the same thing. So you can memorize better. Okay. Actually, suppose we have time later. It's possible to prove. Two different antiderivatives of the same function. They differ by at most a constant. Okay. Yeah, that's why the general form of the antiderivative of cos of x is equals to sine of x and plus c. Okay. Now remember, c is an arbitrary constant. Now we are going to introduce the new concept. Okay. The new concept is using the weird notation. Newton and Leibniz, they discovered calculus at roughly the same time, independently. Okay. Now I'm going to tell you the meaning of this notation. This notation is called the indefinite integral. Now listen to me carefully. We have a new notation. We have a new thing. This notation is called the indefinite integral of cos of x. The term is here. The indefinite integral of cos of x. Okay. The meaning of this notation, I'm telling you the meaning right now. The meaning of this notation is just the most general form of the antiderivatives of cos of x. I want to repeat the meaning. Okay. The notation on the screen, you look at the cursor, the mouse cursor. This notation, it means it's called the indefinite integral of cos of x. The meaning of this notation, or the meaning of the indefinite integral of cos of x, is the most general form of the antiderivatives of cos of x. So the answer to that is equal to. So the meaning is the same thing as the meaning in question 5. We have answered question 5, right? The most general form of the antiderivative of cos of x. Okay. So the answer is sine of x and then plus c. Okay. That's the new concept. Simple, right? I think you have seen this notation over and over again, probably in different other courses. Now you know the meaning. Okay. After introducing the concept of indefinite integrals, I will tell you some terms. I will tell you some names. Okay. This weird notation is called the integration notation. This notation is called the integration notation. And the function inside the integration notation, so this function is called the integrand. And of course, x is called the integration variable. Okay. So do not forget dx. The whole thing is, I'm trying to say, dx is part of the integration notation. Dx is part of, you just treat the whole left-hand side. You just treat the whole notation, the whole thing, as a whole notation. I'm trying to say, do not forget dx. Dx is part of the integration notation. Okay. For the first few questions, it's super easy to forget dx. Okay. I'm trying to say, do not forget dx. Okay. In general, how to calculate the indefinite integral of a function? It's easy. It's always the same. In order to evaluate or to compute the indefinite integral of a function, all we need is to get a particular antiderivative of the integrand. In this particular case, sine of x is a particular antiderivative of the integrand cos of x, right? And then you plus c. I'm going to repeat, okay? To evaluate the indefinite integral of a function, all we need is to find a particular antiderivative of the integrand and then plus c. In the answer, do not forget to plus c. In the answer, do not forget to plus c. Okay. So now let's say if the whole question is worth 10 points. If you forget plus c, I can give you 0.1 points. Why? So because the meaning of the integral is the collection of all the antiderivatives of the integrand. If you forget c, then you just give me 1, so you miss many. So do you know what I mean? I'm trying to say, do not forget plus c, so do not forget dx. I was trying to point out the two common mistakes of people who just start to do integrals. Alright. Any questions so far? Simple, right? You just remember one thing: to evaluate the indefinite integral of a function, all you need is to get a particular antiderivative of the integrand, and then plus c. Do not forget dx, so do not forget c. So that's all. That's all I said. Okay. So you know you are going to have many basic formulas to memorize. I'm going to release all the integration formulas at once. Maybe I'm going to tell you why very shortly, but try to memorize all the basic formulas. On the screen, you have a PDF file containing, I don't want to say consisting of, containing all the basic formulas I want you to know. Try to memorize all the basic formulas by Wednesday. Okay. And then I'm going to make some comments and I'm telling you how to memorize. Okay. Now, for instance, now get your phone, so take a picture of the screen, like the basic formulas for differentiation. Now you have all the basic formulas for integrations. Okay, for integration. Now get your phone, so take a picture of the screen. Actually, you have a few more. I think you have at least 3 more. On the next page. Okay, now I'm going to make comments on how to memorize the basic formulas. Actually, if you know what's going on, you really do not need to memorize, as long as you know the concept. Okay. I'm trying to say, actually, each basic differentiation formula will correspond to a basic integration formula. Okay. Now, for instance, I just told you why the formula in item number 9 is true. Okay. Now, for instance, I'm trying to say to evaluate the indefinite integral of cos of x, all we need is to find a particular antiderivative of cos of x. So you just think which function has the derivative of cos of x, like we did in part 2. Okay. You told me sine of x has the derivative of cos of x. That's why sine of x is an antiderivative of cos of x, right? So to evaluate the indefinite integral, all we need is to get a particular antiderivative of cos of x, so which is sine of x, and then you add a constant, arbitrary constant c, so you have the answer, right? And likewise, okay. Now, for instance, the same is true for number 10. You look at number 10. If you are trying to evaluate the indefinite integral of secant squared of x, all we need is to get a particular antiderivative of secant squared of x. So you think which function has the derivative of secant squared of x? You know that. You know it's tan of x, right? So because the derivative of tan of x is secant squared of x. That's why tan of x is an antiderivative of secant squared of x. Get a particular antiderivative, and then you plus c, the arbitrary constant, and then you're done, right? Actually, the same is true for all other formulas. So now let's say for formula number 6, antiderivative of e to the power of x, you think which function has the derivative of e to the power of x? Okay. I'm trying to say e to the power of x is an antiderivative of e to the power of x. That's why the indefinite integral of e to the power of x is equal to e to the power of x. Okay. Actually, the same argument is true for all the basic formulas. Now let's take a look at a little bit different one. Okay. Now you look at item number 8. In item number 8, in order to evaluate the indefinite integral of sine of x, you think you need a particular antiderivative of sine of x, right? So you think which function has the derivative of sine of x? It's negative cos of x. It's not cos of x. The derivative of cos of x is negative sine. The derivative of negative cos of x is sine of x. That's why negative cos of x is a particular antiderivative of sine of x. You use a particular antiderivative of the integrand, and then you plus c, you have the answer. Again, so do not forget c, so do not forget dx. I think the only formula that might be a little bit weird is the thing in item number 5. The thing in item number 5. I will copy this formula. So how about temporarily you just remember in order to get the indefinite integral of 1 over x, the answer is natural log of the absolute value of x and then plus c. So do not forget there's an absolute value of x in here. So maybe I can tell you why so very quickly. Yeah. I'm going to tell you why. Why? So there's an absolute value sign involved in here. So very quickly. Okay. Actually, to show the formula is true, we divide the whole thing into 2 cases. Okay. We divide the whole thing into 2 cases. You know, on the right-hand side, natural log is defined only when whatever thing is positive. I'm trying to say natural log of any negative number is undefined. So natural log of 0 is undefined. is undefined as well. Okay, so we divide the whole thing into two cases. Okay, if so now let's say x is a number, a positive number, and then if you take the derivative of so natural log of x, you know it's 1 over x, right? So in this case, in the case that x is positive, so natural log of x, which is the same thing as natural log of absolute value of x. So because x is positive, x is the same thing as the absolute value of x. Okay, is a antiderivative of 1 over x. So that's true when x is positive. Actually, the same formula is true. Is also true when x is negative. Okay. So now let's say x itself is negative, and then so take a look at this. Okay, natural log of the absolute value of x. You just imagine x is a number like so -5, so -10. Natural log of the absolute value of x is actually, in this particular case, is actually natural log of so -x. So because x itself is negative. Okay. So in this case, we want to show the underlying function is actually an antiderivative of 1 over x, right? So natural log of the absolute value of x, you take the derivative of that, is actually the same thing as natural log of you take the derivative of natural log of so -x. Okay. For this one, we have to use the chain rule, right? For this one, we have to use the chain rule. You choose u to be the whole thing. So in the brackets, you have 1 over -x, 1 over u. Your u is -x. Okay. Working from outside to inside. Okay. And then you take the derivative of the inside function, so which is the derivative of -x. So do you see you also have 1 over x? What I'm trying to say is that when x itself is negative, the natural log of the absolute value of x is an antiderivative of 1 over x. Okay. For the first case, so probably if x is positive, you have seen natural log of the absolute value of x is an antiderivative of 1 over x as well. Now we combine the two cases. To get the indefinite integral of 1 over x and then times dx. All we need is to get an antiderivative. In both cases, the antiderivative can be represented in terms of natural log of the absolute value of x, right? And then plus c. Okay. If you cannot follow me, it doesn't matter. The bottom line, you just remember the bottom line. To compute the indefinite integral of 1 over x, the same as before, you get a particular antiderivative and then plus c. So just in this particular antiderivative, you remember there's an absolute value of x involved. Okay, so that's it. Actually, now I think you see why item number 3 is also true, right? It's true. So because kx, you treat k as a constant. K times x is a particular antiderivative of the constant of k. You know, you take the derivative of kx, you have k. So kx is an antiderivative of the constant of k, right? Yeah, so that's why the formula is true. Okay. The only formula I'm going to make many more comments is number 4. This is the formula for handling how to compute the indefinite integral of power functions. Now remember n value exponent is not equal to -1, because when n value is -1, the case in item number 5. We have a separate formula to handle that case. Okay. You just remember this is the case when n exponent is not equal to -1. Okay, and then you have a formula for computing the indefinite integral of any power function when n value is not equal to -1. Okay. To show the formula is true, the same thing, you take the derivative of the right hand side. Now let me show you why, and then we are going to use a few questions to illustrate how to use that formula. Okay. In order to see why the formula is true, all we need is to show this function is a particular antiderivative of the function. So by that we mean all we need is to show the derivative of this function is equal to the integrand. Okay. The formula is true. So because what? We want to show the derivative of the right hand side, the function on the right hand side is equal to the integrand. Okay, so we just show that. Okay. So can I write the inside function in slightly different form? It's actually 1 over n plus 1, and then times x to the power of n plus 1. You take the derivative of that. Okay. So you leave out the constant of 1 over n plus 1. Okay. And then you compute the derivative of x to the power of n plus 1. And then times, you use the power rule. Okay. You use the power rule for x to the power of n plus 1. I think you can see you have n plus 1 and then times x to the power of n, the power rule for differentiation. Okay. N plus 1 and n plus 1 is cancelled, so you have x to the power of n. Okay. Okay, so because the derivative of that function is equal to x to the power of n, I'm trying to say this function, you look at the mouse cursor, okay? This function is actually a particular antiderivative of x to the power of n. In order to evaluate the indefinite integral of x to the power of n, all we need is to get a particular antiderivative of the integrand and then plus c, right? So that's why, so this formula is true. In the future, it's always so the same thing. No matter how complicated the integrand is, for an indefinite integral, it's always possible for you to check the answer on your own. By that I mean you differentiate the right hand side as long as the derivative of the right hand side is the integrand, and then your answer is right. Okay. I was just trying to tell you why many of these formulas are true, starting from number 3 to item number 15. Okay. And then for the power rule, I'm going to use some particular questions to make more comments on the power rule. And then I'm going to make some comments on item number 1, item number 2, the two properties. After that, we are going to be ready to deal with the handout questions. Okay. So that's the plan. I will copy the power rule to this corner. Okay. The following questions are designed for the power rule. Okay. Actually, for the power rule, the comment I want to make now is that n is not necessarily a positive whole number. I'm trying to say n can be any real number. Actually, n can be any decimal number, n can be any fraction, n can be any negative fractions. Actually, n can be any real number. To make my point, so we're going to try some questions. So maybe a little bit quicker. Okay. So maybe anybody want to tell me the answer to this? X squared. Now we're trying to compute the indefinite integral of x squared. I showed you the answer earlier. You could think of the question in two ways. One way is which function has the derivative of x squared. You get an antiderivative, right? And then you plus c, you can have the answer. But now we're kind of practicing the power rule. Okay. This is the particular case that n value is equal to 2. Now all we need is to use the power rule, okay, for n value of 2. Anybody want to tell me a particular antiderivative of the integrand x squared? This is a particular case that n value is 2, okay. You know that, right? So the answer is x to the power of 2 plus 1, so which is x to the power of 3. On denominator you have n plus 1, you have 3, right? So the answer is actually x cubed and then over 3 and then plus c. Okay. That's one of the questions I want to go over. Simple, right? I want to repeat the two things I mentioned before, okay? Dx is part of the integration notation, so do not forget dx. And also, using the meaning of indefinite integrals, we are looking for the most general form of the antiderivatives of x squared. So do not forget c, I'm trying to say. Okay, now let's try another. So now let's say x to the power of 100. The whole thing is called the indefinite integral of the function x to the power of 100. This is a particular case that n value is equal to 100, right? Anybody try to answer my question? So what is a particular antiderivative of x to the power of 100 and then plus c, you have the answer. Try something, please. Okay. I think people in this class normally answer questions, but I don't know why recently. Anybody want to tell me a particular antiderivative of x to the power of 100? And then with plus c we have. Sure, thank you. Cool. Sure, thank you so much. So you're following me. Okay, it's x to the power of 101, right? And then on denominator you have 101 and then plus c. Okay, these two cases are simple enough. Okay, so do not forget to plus c. Do not forget to plus c. Okay, and then now we're going to make the thing a little bit more complicated. Okay, you know the power functions consist of many radical functions and many other functions as well. Okay, so how about so we'll try this. If the numerator is 1, it's permissible to write dx on top. I'm trying to say if we're trying to write the indefinite integral of 1 over x to the power of 10, we can write the whole thing in that form. Okay. You know, the integrand is 1 over x to the power of 10. It's essentially a power function. We want to use the formula. We want to use the power rule. So, but before using the power rule, the same as before. Okay, I think we have seen that in the differentiation, right? The first thing we do is to rewrite the integrand to the form of a power function. Okay, I'm not getting the antiderivatives yet. Okay, I'm just trying to rewrite the integrand to the form of a power function. It's x to the power of negative 10, right? And then, so do not forget dx. Okay. So what do we do next? Now we can apply the power rule. Okay. This is a particular case that n value is negative 10. Okay. N value is negative 10. Now we're ready to get the answer. Now we use the power rule. We have x to the power of n plus 1. In this particular case, it's negative 10 plus 1. Okay, it's negative 10 plus 1. You have so negative 9. Negative 10 plus 1. You have negative 9, right? If exponent is negative 9, I'll tell you a little trick. So can I rewrite the basic formula in some different form? It's x to the power of n plus 1, and then the number coefficient before that can be written as 1 over n plus 1, okay, and then plus c. I'm trying to say the coefficient in the box is always the reciprocal of exponent in here. Okay, it's actually true in general. I'm telling you a little trick now. Okay, if in the antiderivative exponent is negative 9, the number before that is always the reciprocal of exponent, so which is negative 1 over 9. So do you know what I mean? It's negative 1 over 9 and then plus c. You could see that from the basic formula, or you could remember the rule. So what I just told you. Okay. Again, the coefficient after applying the power rule, the coefficient is always the reciprocal of exponent in here. I use two boxes, so can I use the circle here? I mean, the stuff in the box is always the reciprocal in the circle. If you can remember that, then later on many other calculations are simple. Okay. Now I'm going to show you one other, and then you can try some more. Okay. So maybe for question number 4, I'm going to. So how about we do this? We do, so now let's say square root of x and then dx. Okay. You know, square root of x is essentially a power function. So because it can be written in the form of a power function, right? So to get the indefinite integral of square root of x, so the first thing we do is the same as before. We convert the function to the form of a power function so that we can use the power rule. Okay, square root of x is x to the power of 1/2. So we have seen that over and over again, right? So this is a particular case that n value is equal to 1/2. Use the power rule for integration. So do not use the power rule for differentiation. Okay, you use the formula on this corner. Okay. Get the power function part first. Okay, so I'm trying to say get x to some power first. Okay, this is a particular case that n value is equal to 1/2. So in the antiderivative, in a particular antiderivative, exponent part is 1/2 plus 1, n plus 1, n value is 1/2. So the exponent part is 1/2 plus 1, n plus 1, so which is 3 over 2, right? 1/2 plus 1 is 3 over 2. I think you can do it mentally. Okay. If the exponent here is 3 over 2, then you invert the numerator and the denominator of 3 over 2. You have the reciprocal, right? So the coefficient before the function is 2 over 3. So do you know what I mean? It's simple now. You do not have to. You just remember the coefficient is always the reciprocal of exponent, you invert the numerator and the denominator. You can have the coefficient, and then you plus c. Okay. Simple enough. As long as you know how to convert the radical functions and the many other functions to the form of a power function, then you use the formula, the questions are simple. Okay. Alright. I'm not going to run too fast for this one, because okay, it's the first time you see integration stuff. I do want to make sure you get used to the notations and so on. Okay. Now I want you to try at least 3 questions. Try, please. Okay. You try a little while and then we compare the answers. Okay. So maybe the first question I want you to try is so how about we do the indefinite integral of x to the power of 10? A simple one first. Okay. And then the second one I want you to try is x to the power of 10 on denominator. So did we do that? So how about so this time I give you x to the power of 100 on denominator. I remember the question I did. I will give you a slightly different one. Okay, now I'm going to make some comments. I think you have that. So question 1 is simple, right? It's a particular case that n value is 10. It's straightforward. Exponent part is x to the power of 11, 10 plus 1, right? And then you get the reciprocal of exponent. You have the answer. And then question number 2. The first thing you do is to convert the function to the form of a power function. You know that 1 over x to the power of 100 is x to the power of negative 100. Okay. And then you use the power rule, okay, for integration. Exponent part is x to the power of n plus 1. Negative 100 plus 1, you have negative 99. Okay. And then if exponent is negative 99, then the coefficient, I mean the number before the function, is the reciprocal of negative 99, so which is negative 1 over 99, right? And then plus c. For question 2, I made a mistake on purpose. Anybody want to tell me the mistake, a notation problem in question 2? Anybody want to tell me what I missed in question 2? dx. Sure, thank you. So don't forget dx is part of the integration notation. So do not forget dx. On Wednesday, you are going to see better why you have to include dx. Okay, when we do the substitution rule. Okay, you are going to see it's essential to have dx in the integration. So question number 3 is kind of the same story. Okay. Essentially, the integrand is a power function. So just when the numerator is 1, you can put dx on the numerator. Okay. In any case, the first thing we do is to convert the function to the form of a power function. I was not trying to make a mistake in here. I hope I got it right. And then using the power rule for the integration. Okay. You get a particular antiderivative of the integrand. This is a particular case that n value is negative 2 over 3. Okay. In the antiderivative x to the power of n plus 1, negative 2 over 3 plus 1, you have 1/3. Right. And then if exponent is 1/3, and then the number before that is you invert 1 and 3, you have 3, right? I'm trying to say the reciprocal of 1/3 is 3. Yeah, I think the book has seen what I did wrong. I was trying to miss the C. That's actually another common mistake for the people who just started to do integration stuff. So do not forget C. Do not forget C. Okay. All right. I think these are enough questions for practicing the power rule for integration. And then after I make some comments on item number 1 and item number 2, we are going to be ready to do the handout questions. Okay. Now you look at property number 1. It kind of says c is a constant, f of x is a function. Okay. If you have a constant factor in the integrand, it's permissible to leave out the constant, out of the integration notation. It's kind of saying that. Okay. For property number 2, it says actually the same property is true if you replace addition with the subtraction. Okay. It says the integral of the sum of two functions is equal to the sum of the two integrals. I'm going to use some particular functions. I'm trying to use some particular integrals to show the meaning. Okay. How about I just copy the two properties to the PowerPoint, so you'll see what we are doing. Okay, now item number 1. To illustrate item number 1, I'm going to use a particular question to show you the meaning. So now let's see. If I want you to evaluate the integral of, so now let's say 3 times, so now let's say cos of x. You see in the integrand you have a constant factor of 3. Using property number 1, we said it's permissible to leave out the constant of 3, to leave the constant factor out of the integration notation. So I'm trying to say, you look at property number 1. we leave 3 out of the integration notation. Okay, so you have the integral of cos of x and then dx, right? Now you look at the basic formulas. Okay, the integral of cos of x is in the basic formula. Okay, so you have 3 times. In general, you have 3 times the indefinite integral of cos of x is a particular antiderivative of cos, so it is sine of x, right? And then plus, should I use c? So can I use c1 to denote an arbitrary constant? And then the final answer is going to be so something like 3 times sine of x and then plus 3c1. The following is kind of so important. You just imagine if c1 denotes an arbitrary constant, and then 3c1 is also an arbitrary constant. I'm trying to say if you let c1 run through all the real numbers, and then 3c1 also run through all the real numbers. I'm trying to say 3c1 now can be replaced with c. You do not have to write 3c1. So the answer can be so something like 3 times sine of x and then plus c. I was replacing 3c1 with one constant of c. Okay. So that makes sense? I want to repeat, if c1 runs through all the real numbers, then 3c1 also run through all the real numbers, also denotes any real number. Same thing. Okay. So that's a question illustrating the meaning of property number 1. Okay. Can I just label the question using, so it doesn't matter. Okay. The following question is designed to illustrate how to use property number 2. Okay. Again, property number 2 says the indefinite integral of the sum of 2 functions is equal to the sum of 2 integrals. Again, I'm going to use a particular question to illustrate the meaning. Okay. So how about we compute the indefinite integral of, so now let's say e to the power of x and then plus cos of x. So dx. So do not forget dx is part of the integration notation. Actually, many people do not use brackets in this context, but I still do not feel comfortable without using brackets. I'm trying to say, if you're trying to evaluate the integral of the sum of 2 functions, I prefer to use the brackets to enclose the sum of the two functions. If you are going to some universities in September, you are going to see some instructors, so do not do that. I still don't feel comfortable without including the brackets. Okay, now the question is designed to illustrate property number 2. Okay, so property number 2, you see now we're trying to evaluate the integral of the sum of 2 functions. Using property number 2, it's going to be converted to the sum of 2 integrals. Okay, one integral is the integral, so now let's say e to the power of x and then dx, so do not forget dx again. Okay, and then plus the integral, the indefinite integral of cos of x, so dx, right? Okay, and then you look at your phone. I told you to take a picture earlier. The indefinite integral of e to the power of x, you just look at the basic formula. Okay, it's e to the power of x and then plus, can I write c1? Okay, and then the indefinite integral of cos of x is sine of x, right? You need a particular antiderivative of cos of x, which is sine of x and then plus another c2. Okay. For the same reason, you can combine C1 and C2. You can replace C1 and C2. I'm going to write that in one more step, okay? It's e to the power of x and then plus sine of x, right? And then plus C1 and then plus C2, okay? For the same reason, if C1 denotes an arbitrary constant, and if C2 denotes an arbitrary constant, C1 plus C2 also denotes an arbitrary constant. Okay, I'm trying to say you can combine C1 and C2 with this to a new constant of C. Okay, so the final answer, you can write the final answer as e to the power of x, and then plus sine of x, and then plus sine of x. And then plus c. By default, c is an arbitrary constant. You do not have to state that. All right. Now I'm going to combine the two properties in item number 1 and item number 2. Okay. And we're going to do it's kind of called a linear combination of the two functions. We do not introduce a term. So how about we just look at one other question before we take a little break. Okay. Can I move on a little bit further before we take a little break? So today, for some reason, you are going to see shortly. Okay. The next question I'm going to talk about is, so how about we compute 2 times, let's say e to the power of x, and then plus 3 times sine of, let's say cos of x. And then dx, so do not forget dx is part of the integration notation. Okay. For this question, we're going to repeatedly using the two properties. So the first thing, so how about we use a subtraction here? I told you the property is true for addition and for subtraction. Okay. I'm trying to say property number 2. Property number 2. Property number 2 is true for subtraction as well if you replace addition with a subtraction. Okay, so to do that, so probably the first property you want to use is the property for the subtraction. Okay, you convert the integral to the two integrals. You have 2e to the power of x, and then dx in here, minus 3 times cos of x, and then dx here. Okay, and then you use property number 1. Okay, you can leave out constant. You can leave out the arbitrary constant of 2. Okay, leave out the arbitrary constant of 2, you have the integral of e to the power of x, so dx is here, minus, you leave out the constant 3, the constant factor of 3. You leave the constant factor of 3 out of the integration notation. You have 3 times the indefinite integral of cos of x, right? And then you have 2 times, it's in the formula now, okay? You know the indefinite integral of e to the power of x, which is e to the power of x, and then plus, can I use c1? A constant c, an arbitrary constant c, okay? And then you also have minus 3 times, now let's say, antiderivative of, the indefinite integral of cos of x is equal to sine of x, and then plus c2, right? I'm using c2 to denote an arbitrary constant. I'm trying to say, in the final answer, okay? In the final answer, you are going to get something like the following: 2 times e to the power of x, and then plus 2c1, and then minus 3 times sine of x, and then minus 3c2. So do you see that? Finally, we are going to get, now let's say 2 times e to the power of x, and then minus 3 times sine of x, and then plus 2c1, and then minus 3c2. Again, for the same reason, c1 is an arbitrary constant, and the c2 is also an arbitrary constant. So you can see it's 2c1 and then minus 3c2 is also an arbitrary constant. I'm trying to say I can replace the whole thing in the box with a constant of c, with one constant of c. So the final answer is going to be 2 times e to the power of x minus 3 times sine of x, and then plus one arbitrary constant of c. Okay. This question is designed for repeatedly using the two properties. You have seen we have repeatedly using the two properties. Now a good news for you, okay? Now you listen to me carefully. In the future, as long as you know what's going on, in the future, as long as you know where the properties are used, in the future you can remove everything in that box. It's permissible to do the question from the beginning to the end. I'm trying to say it's permissible to do the question in one step. Listen to me carefully. Now I'm telling you how to do the question in one step. Okay, how can we do the question in one step? In order to get the indefinite integral of the integrand, temporarily you ignore the constants. You ignore the constant factors. I'm trying to say you get a antiderivative of e to the power of x. Look at the basic formula. An antiderivative of e to the power of x is e to the power of x. Look at the basic formula, okay? And also you locate the antiderivative of cos of x, so which is sine of x, is in the basic formula as well. Okay, and then you use the corresponding constants as the coefficients in the answer, in the antiderivative, I mean. Okay, that's how you get a particular antiderivative of the function. After getting that, you add an arbitrary constant c. After that, you add an arbitrary constant of c. So you have the final answer. Okay. All right. After this comment, we are ready to do the handout questions finally. Okay, now I'm going to use the idea I just told you. You do not have to write many steps. You can just do the question in one step. Okay. As long as you know what's going on, it's simple. Okay, it's simple. For this question, you do not even have to convert the function to the form of the power functions. Okay, use the formula for the power rule. Now we can get a particular antiderivative of x squared. Anybody want to write a particular antiderivative of x squared? Using the power rule formula, get a particular antiderivative of x squared first. I think you don't bother, you know that. Okay, it's x cubed over 3. We have seen that many times, right? And then for the underlined term, for this function, for this integral, I'm trying to say you do not even have to convert the function to the form of a power function. Now you concentrate on the underlined function. Which function has the derivative of the underlined function? Which function has the derivative of negative 1 over x squared? I told you to memorize it before, right? It's plus 1 over x. I'm trying to get a particular antiderivative of negative 1 over x squared. It's positive 1 over x, because the derivative of 1 over x is the underlined function. So that makes sense? So that's why 1 over x is a particular antiderivative of negative 1 over x squared. Now you look at the box function. Okay, the function in the box. Which function has the derivative of the function in the box? I'm going to repeat my question. Which function has the derivative of the function in the box? That will give you the answer to that will give you the antiderivative of the function in the box. That's the square root of x, right? And then you think which function has the derivative of 5? You have 5x. I'm trying to say in the integrand you have 4 terms, and then you get a particular antiderivative for each of the 2 terms, for each of the 4 terms. Okay. After that, you plus a arbitrary constant c. You have the final answer. Actually, that's one way to do it. So the other way to do it, I'm going to tell you the other way. If you cannot get antiderivatives easily, okay. The other way to do it is I'm going to copy the function. So maybe I can copy the function again. I just say way number 1 to do it. And then the second way to do it is I just said I would copy the function again. The second way to do it is to rewrite all the terms in the integrand in terms of the power functions. One function is x squared, and then minus the second function is 1 over. So not 1 over. We convert 1 over x squared to the form of a power function, to the form of x to the power of negative 2, right? And then the third function is plus. So maybe we leave out 1/2. 1/2 times x to the power of negative 1/2. So do you see the third term is converted to a function like that? So because 1 over square root of x is x to the power of negative 1/2, right? And then so there's nothing you can do about 5. I'm trying to say the second way to do the question is the first thing you do is to convert all the terms to the form of a power function, okay? To the form of power functions, I mean, okay? After doing that, it's possible now to get a particular antiderivative of all the terms, of each of the 4 terms. Antiderivative of x squared, you have x to the power of 3. N value is 2, right? X to the power of n plus 1. If exponent is 3, the coefficient is 1/3. Reciprocal, right? And then to get minus sign, you copy the minus sign, right? And then for the box term, it's a particular case that n value is equal to negative 2. You use the power rule for integration, okay? Antiderivative of x to the power of negative 2 is equal to x to the power of negative 2 and then plus 1. N plus 1, n value is negative 2. You have negative 1, right? If you have a negative 1 here, then you have a negative 1 as a coefficient. I'm not going to to simplify even. Okay. For this type of the questions, you do not have to simplify. And likewise, the antiderivative of the next term, you leave out the constant of 1/2. You get antiderivative of the underlined function x to the power of negative 1/2. So for that, you have x to the power of, this is a particular case that n value is negative 1/2. Negative 1/2 plus 1, you have positive 1/2, right? If you have a positive 1/2 here, then the number before that is 2. So that makes sense? The reciprocal of 1/2 is 2. And also antiderivative of 5. You have a basic formula, okay? Or alternatively, you think which function has the derivative of 5. You have 5x and then plus c. Okay. The second way to do the question is permissible too. Okay, you do not even have to simplify. I'm trying to say even for the term like x to the power of 1/2, you do not have to convert them to the form of square root of x and so on. Okay. I did question 1 in 2 ways. Now you look at question 2. I think the only way to do question 2 is to convert the radicals to the form of the power functions before you use the power rule. Okay. And question 3, 4, and the question 5 and 6 are all designed for the basic formulas. So maybe some comments on question 2. Okay. I did not make any mistake on purpose. Now look at the question 2. Okay. The first thing you do is to convert the radical functions in the two terms to the form of the power functions. Okay. Now let's say the first term is 5th root of x to the power of 4 is converted to x to the power of 4 over 5. All of you guys know that. And then you copy the constants, right? I mean, copy the constant factors. And the same thing is true for the second term, x to the power of negative 4 over 3. I think I got this right. As I said earlier, it's permissible to get antiderivatives, so term by term. You just copy the constants and copy the constant factor of 2 to here. Okay. To get antiderivative of x to the power of 4 over 5, you compute exponent first. I mean, you get x to the power of n plus 1 for the n value of 4 over 5, right? 4 over 5 plus 1 is 9 over 5. If you see 9 over 5 in here, you invert numerator and the denominator, you have 5 over 9 in here. So do not forget the constant factor of 2. Okay. And the same thing, you can do the same thing for the next term. All right. Any questions about question number 2? Of course, you could multiply 2 times 5 over 9. You can combine these two numbers to 10 over 9. You can combine these two numbers to 12, so the same thing. And I think question 3 is designed for the basic formulas as well, so no tricky stuff. Okay, so just the antiderivative of x cubed, antiderivative of x squared, you use the power rule for integration. You have x cubed over 3. I just put 3 here. It's because I want to put the numbers together. Okay. And then antiderivative of 4, the constant of 4 is 4x. It's straightforward. Okay. I think I don't have any comments on question 4. It's straightforward. For each term, without looking at the constants, without looking at the constant factors, you have formulas for getting the antiderivatives of all the terms. And the same is true for question number 5. So just do not forget antiderivative of 1 over x. In antiderivative of 1 over x, there's an absolute value of x involved. So do not forget that. Okay. And the last term is straightforward too. Antiderivative of 5 to the power of x. You look at the basic formula. It's a particular case when a value is 5. Antiderivative of a to the power of x is a to the power of x over natural log of a. This is a particular case that a value is 5. Alright. And again, for the antiderivative of term 3, do not forget the absolute value of x.